Welcome back to the deep dive. Today, we're tackling a concept that, on the surface, looks like pure technical code, user-defined functions.
Mm,
But we're going to show you why this isn't just about programming. It is, well, it's absolutely foundational to being an efficient, modern knowledge worker.
that's really the mission today. Yeah, we've taken a stack of source material on the mechanics, the utility, all the data management aspects of functions.
And the goal.
The goal is to get past the syntax
Hmm.
and really transform this into a strategic tool for breaking down any complex problem, whether you're coding or, just building repeatable processes.
Okay, let's jump straight in. What is this?
Hmm.
This fundamental building block. The sources define a function as a named sequence of statements that all run together to solve one specific task.
It's like giving a label to a tiny custom-built machine.
Yeah.
And what's fascinating here is that the idea itself, it's not new. It's much older than computers.
Oh, really?
It's borrowed directly from algebra.
Oh,
When you first learned about f of x, you were actually being introduced to the concept of a function.
that makes the abstract idea instantly accessible, doesn't it?
Precisely. The function defines the rule, the machine's logic. So if our algebraic function is, say, f of x equals x squared plus x plus 1, that formula is the definition.
And then you call it.
Exactly. You call it by plugging in an input, like x equals 1. The output, the result, is 3. But you can use that same definition, that same machine, to solve for x equals minus 2, and the output is still 3. The rule stays the same.
So there's a necessary two-step process here. First, you have to define the function, build the machine, give it a name.
Right.
And second, you have to call it, feed it data, and hit run. If you try to call something you haven't defined, you get an error. Simple as that.
And in that definition stage, there are a couple of small rules. The function name, it follows the same rules as a variable name, make it descriptive.
Okay.
And critically, the sources confirm that things like parameters and a return statement are actually optional when you first define it. A function can just be a simple named container for logic.
But that leads to the foundational question, right? Why bother? Why go through the effort of defining this separate block of logic?
When you could just write it all out in a line.
Yeah, exactly. Why should you spend time creating a shortcut?
Well, the advantages aren't. They're not marginal. They are really the difference between scalable and unscalable work. It boils down to clarity, reusability, and maintainability.
Okay, let's start with clarity. Functions let you hide complex logic behind a simple name. So instead of scrolling through 50 lines of calculations, you just see one line, calculate slope.
Instant understanding.
It's immediate clarity. And that links directly to debugging, doesn't it?
Oh, absolutely. If you write a massive 500-line program without any functions, finding one tiny error can be a nightmare. Everything is tangled together.
I've been there. It's not fun.
No. But functions encourage isolation. You could debug your format report that or function all by itself, test it, and once you know it works, you just don't have to worry about it again.
Right, you can cross it off the list of suspects if the bigger program fails. I think the most visceral win for me, the thing that sells the concept instantly, is just eliminating repetition. We've all done it. Copying and pasting the same block of code over and over.
10 times. And then you realize there was a tiny flaw in the original logic.
Oh, the worst.
Now you have to go find all 10 of those copies and manually update every single one. It's just asking for trouble.
Exactly. But when you put those steps into one single function, you only have to make that change in one place. You fix the function, and bam, all 10 places are fixed instantly.
And that's efficiency. It makes the program smaller and way more resilient.
So this reusability is the key idea for the knowledge worker to really internalize.
Yes, this idea of write once, test, share, and reuse many times is the engine behind all modern software libraries.
Yeah.
You don't rewrite how to calculate a square root every single time you do
We
it.
call the function someone else already wrote and tested.
Ex-
And if we think beyond coding, this applies everywhere. Like a complex spreadsheet macro or a standard operating procedure, an SOP in your company.
Good example.
You define the complex part, say the data validation step, as a separate process, a function. Then you don't rewrite those validation steps in every SOP, you just reference the named process.
You fix the process once, and every SOP that uses it is instantly updated. That is the strategic value.
So functions are the shortcut.
They're the shortcut to organizational knowledge and efficiency. They force you to break a big, overwhelming problem into smaller, manageable, reusable pieces.
Let's pivot to the mechanics of that reusability. We need to talk about what functions actually produce, because not all of them give you an answer, right?
That's right. The sources draw a clear line between two main types. I like to think of them as action functions and calculation functions.
Okay, I like that framing way better than fruitless and fruitful. Let's start with action functions.
Action functions, or what are sometimes called void functions, they don't explicitly return a value. Their whole purpose is to do something, to perform a task.
A side effect.
A side effect, exactly. They might print something to the screen or save data to a file. They perform an action, but they don't hand you back a number you can use in an equation.
Got it. So now, calculation functions. These are the ones designed to produce a result.
Correct. These are the functions that use that return statement to explicitly hand back one or more values. If you're doing math, data analysis, anything like that, these are your workhorses.
And they're really useful because the answers they give can be used to solve even bigger problems.
And they are so much easier to test because they give you a defined output to check against.
Okay, there is a critical detail about that return statement that always trips people up. It's more than just providing an answer. It's like an immediate stop sign.
It is. It's a mission accomplished signal. The moment the program hits return, the function stops, dead in its tracks, and hands the value back.
So any code after the return statement is just ignored.
Completely ignored, skipped, even if it's perfectly good logic. And this is actually super useful for returning early if you detect an error, so you don't waste time processing bad data.
Makes sense. Okay, so functions either take an action or give us a calculation. Now we need to figure out how we get data into the machine in the first place.
Right, through parameters and arguments. This is where we define the function's interface with the outside world.
The sources are clear that a function can take 1, 0, or many parameters.
Yep. The parameters are the placeholders in the function definition, what it expects to get. The arguments are the actual values you provide when you call the function.
And we have to distinguish between required and optional data. If a parameter is required, you must provide an argument, or the program will crash.
But you can make them more flexible. You can give a parameter a default value right in the definition. That makes it optional.
So if the user doesn't provide that piece of data,
the function just uses its default setting. But if they do provide it, their argument overrides the default. It's a great way to handle common cases gracefully.
and for complex calculations, a function can return more than one value, which is a huge help.
A huge help. You just list them, comma separated, in the return statement. And here's a crucial detail from the sources. When multiple values are returned, they get packaged together into a single structure, a tuple.
Wait, let's just pause on that word for a second. A tuple. What is that exactly, and why is that the delivery mechanism?
Think of a tuple as a small, unchangeable package for group delivery. It's an ordered collection of items. But the key feature is that once it's created, you cannot change what's inside that package.
Ah, so it provides stability.
Exactly. The values you returned are guaranteed not to be accidentally changed by something else later on. It ensures data integrity.
Okay, that makes perfect sense. Let's move into what I think is the real aha moment for new learners. It's about how data is physically passed to the function in memory.
Yes. This is essential for avoiding some really nasty side effects. Data is passed in one of two ways: passed by value or passed by reference.
Let's start with pass by value. This applies to fundamental things, strings, numbers.
The simple stuff. With pass by value, the actual value of your argument is copied into the parameter inside the function.
So the function is working on a duplicate.
A completely isolated duplicate. If you change the value of that parameter inside the function, you're only changing the copy. The original variable outside is completely untouched. It's safe.
It's predictable. But then we have pass by reference, which is for more complex things like lists or dictionaries.
Yeah.
And this can be risky if you don't know what's happening, right?
That's a valid concern, and it's why this is so important to grasp. With pass by reference, you are not passing a copy. Instead, the parameter inside the function and the argument outside become an alias.
An alias.
They're two different names pointing to the exact same spot in memory where that list or dictionary lives.
So it's not a copy, it's a shared pointer.
Exactly. So if the function modifies that list, say, it adds a new item, that change happens at that shared memory location. The original data structure outside the function is permanently changed.
Okay, let's use an analogy. Pass by value is like handing someone a photocopy of your report. They can scribble all over it, your original is safe. Pass by reference is like giving them a link to the single master Google Doc. Any change they make, everyone sees it. instantly.
That is a perfect articulation of the consequence. And while this is a deep topic, just knowing this memory game exists is key to writing functions that don't surprise you.
So functions are excellent at delegation, and efficient delegation often means one function relies on the services of another.
Oh, yes. The source material confirms a function can absolutely be called from within another function. That's really the cornerstone of building complex, well-structured programs.
Let's look at some of the practical examples from the sources, because this is where the modularity really shines, like a multi-step geometry problem.
Right. One of the exercises involves first writing a function, let's call it slope, that just returns the slope of a line given 4 coordinates. Very specific, very reusable.
And then you build a second function, intercept, to find the y-intercept. But instead of rewriting the whole slope calculation inside it,
You just call your slope function, the one you already built and tested.
so you've created a hierarchy of knowledge. You're leveraging a smaller, tested tool to solve a slightly bigger problem.
Exactly. The person writing intercept only has to worry about the new logic because they trust that the slope tool will always give them the right answer.
Another great example was the time conversion task, calculating seconds into hours, minutes, and seconds, and then formatting it into that HMMSS format.
Yeah, that's not one step. That's a whole bunch of division and remainder math.
Right.
But if you consolidate all that into one function, format times, you only solve that problem once. Then anytime you need to display a duration, you just call that one reliable function. Centralized logic, consistent display.
And this modularity connects directly back to reliability through what the sources call the test factor. Why are functions absolutely necessary for automated tests?
This is a vital connection. Automated tests, which use tools like assert to check for correctness, they demand that logic be isolated. A test needs a defined input, a defined piece of logic, and a verifiable output.
And if your code isn't inside a function, it's hard to isolate the specific logic you want to test from everything else that's going on.
You got it.
Okay.
By putting the calculation inside a function, you're creating a kind of clean room for testing. You feed it a known input, you run it, and you assert that the output is exactly what you expected.
You eliminate all the external noise. So if you're testing a hypotenuse function, you can give it 3, 4, and assert that it returns 5, and only 5.
Exactly. Functions make code verifiable. They hold the logic accountable.
So if we connect this all back to the big picture,
Yeah.
the sources say functions aren't strictly required. You could, theoretically, solve any problem without them. So why do we insist this is a critical mindset?
Because using a function is a choice. It's a choice that transforms a one-off solution into an institutional, reusable asset. You don't need a function to multiply 2 numbers, but choosing to define product, xy, transforms that simple math into a shareable, testable, documented piece of logic.
It's the difference between doing something once versus building a repeatable process.
It is the highest form of efficiency. It saves time and reduces risk for everyone.
That brings us to our summary. To recap the most valuable nuggets. Functions are reusable blocks. Write once, test rigorously, leverage many times. They come in 2 strategic flavors: calculation functions that give you an answer, and action functions that perform a task. And maybe most critically, understanding how data is passed by value or by reference is the key to avoiding unexpected side effects.
And that idea of structured delegation, one function calling another, it opens up some incredible paths. We noted that a function can call other functions, and the source briefly mentioned a concept called recursion. This is where a function calls itself.
To solve a problem by defining it in terms of a simpler version of itself.
Exactly. So here's the thought to mull over. If we accept that functions are the essential tool for breaking problems down, what complex organizational tasks like navigating a deeply nested file system or mapping out a decision tree might require a function that defines itself in terms of a simpler version of itself? That recursive power, it really unlocks the ability to automate some seemingly impossible tasks.
A fascinating path for future exploration. Thank you for guiding us through this essential building block today.
Always a pleasure.